Root locus example 13, root locus analysis. Find the root locus for kgh equals little k over s times s plus 2 times s plus 4. So just like in example 12, the open loop transfer function is really provided for us in the problem statement. And so we can go ahead and provide the open loop transfer function. The only thing that we ever have to worry about is just making sure that it's in its best form. And in this case, there was no change to the form that we needed to actually do. So kgh is equal to little k over s times s plus 2 times s plus 4. And the root locus gain in this case, root locus gain is defined by this uppercase k. That's just equal in this case, in this specific case, equal to little k. Then from the open loop transfer function, we just simply need to provide the poles and zeros. And in this case, very easy to see. There are no zeros, but there are poles at 0, -2, and -4. So very simple approach to finding the poles and zeros for this particular problem. The next is to find the branches, and I've already provided you that there are 3 branches because there are 3 poles. And there are no zeros, so the 3 branches will all terminate at so-called zeros at infinity. And that's important to note because that means that all branches will emerge from the poles and head off to infinity. So we can go ahead and draw the PZ map, the pole zero map, and I'll go ahead and sketch that. So 1, -1, -2, -3, -4, and so there is going to be a pole at 0 right there, a pole at -2, and a pole at -4. So then we'll do what we always do, which is to look at the locations of the branches. On the real axis, there is one branch between the poles of 0 and -2. It's right here. Again, to the right of this branch, there's one pole. That's an odd number. And there are no zeros. So definitely a branch exists. The next place to check is right here, and where I've indicated a branch between -4 and -2, there isn't one, there can't be one, because there is 2 poles plus zeros to the right of that, and that's obviously a even number, so there's not one there. But there is one here, and that one we have 1, 2, 3 poles plus 0 to the right of it. That's an odd number, so that branch does exist there. So I'm going to go ahead and remove all of that marking so that we can draw the asymptotes as well. The next thing is to locate the asymptotes, and we've done a few of these problems before, so I will just provide the expressions for each of those. You can see here the asymptote location is at -0, -2, -4. Actually, I've got this expression wrong that I've included because that should be a negative sign right here. So I'm going to go ahead and remove that, make that correct. So So negative. And there are no zeros, so this is, I went ahead and just put the phrase in there, no zeros, and that just means it's minus 0. So we have minus 2 minus 4 is negative 6 over 3 poles plus 0, or minus 0 zeros, so that's negative 6 over 3, which is negative 2. So the asymptote is going to be right on top of the pole at negative 2. And so I'll just, we'll indicate that in a second. Let's go through the angle, gamma. Gone back to the first formula that I use. It doesn't matter which one you use, but just to give you a little variety, plus or minus 180 degrees, plus or minus 2 times n, 2n times 2 pi being 360 degrees, over 3 minus 0. So immediately we could rewrite this as plus or minus 60 plus or minus 2 over 3 n pi. So what we find, and I can go ahead and just make that a little more clear. So if I get rid of this denominator and just leave with the 2n, whoops. So 180 divided by 3 is going to be 60, and n times 2 pi is going to be n times 2/3 pi. So we'll go ahead and we'll write that as 2/3 pi. So if we look at this, and I can raise this up a little bit, for n, I guess I need to get off the equation, for n equals 0, that's going to be plus or minus 60 plus or minus 0. So that's going to be plus or minus 60 degrees. And then for n equals 1, we have plus or minus 60 plus or minus 2/3 pi. Well, if 2 pi is 360, dividing by 3 will give us 120. So that's going to be plus or minus 60 plus or minus 120, which is going to be plus or minus 180 degrees. If I put n equals 2, that's going to be plus or minus 60 plus or minus 4/3 pi. So that's going to be 120 times 2, or 240. So that's going to be plus or minus 60 plus or minus 240, which is going to be plus or minus 300 degrees. Now, the thing about that is plus 300 degrees is the same as minus 60 degrees, and minus 300 degrees is the same as plus 60 degrees. So now we're repeating. So I'll just write repeats, or repeating, and we can just go with these two. Okay. So what that says is that minus 2, so it's going to be located right there, and we're going to have 60 degrees going up like that, plus 60 degrees, minus 60 degrees going down like that. That's this angle right there. So, and then there's a plus or minus 180. Well, plus and minus 180 are the same thing. It's really along here. So, and like the other problems, we're eventually going to find the breakaway point. Sigma sub b is equal to what? Well, given our branch locations, we know we have a branch here and here. So given that, we know that the breakaway point is going to be between the 0 and the -2. There is no breakaway point at -4 after -4. So I'll just go ahead. I'm going to pick a different color. I'll pick a blue color. So there's going to be a branch here from -4 going off to infinity. And these two at -2 and 0 are going to come together. Now I don't know where it's going to be, but I know it's going to be somewhere between them, and it's going to break away and do this. And at infinity, these blue lines are going to be tangential to the asymptote lines. So that's the basic shape that this is going to be. Again, if you're just sketching this on an envelope, the back of an envelope, back of a napkin or something like that, this is going to be good enough. Is it going to be even between them? Doubtful. It's going to be one side or the other directly in the center between -2 and 0, but it's close enough. So our next step is just to do the actual breakaway points. So we can go ahead and write the expressions for the breakaway points. Here they are, and you can see that the expression is rather simple. There's no zeros, so no zeros, if you can read that. So this is just going to be 0. So there's only sigma sub b plus 0, 1 over sigma sub b plus 0, 1 over sigma sub b plus 2, and 1 over sigma sub b plus 4. Do what we've done before, and so we can get a nice polynomial. It's a second order polynomial. So that's going to give us two possible breakaway points. Well, we know that there can't be a breakaway point between at -3.5. -3.5 would be in this region right here. So it's not going to be there. So that throws out that one. And I can go ahead and just X that one out. So it's not going to be that one. So it's going to be this -0.845. And that makes a lot of sense. So it's going to be located, so here's -1 right there. So it's going to be just to the left of that, maybe a little more than halfway between -1 and -2. So, so obviously the breakaway point occurs closer to the -2 pole. And that provides us that makes a little sense to us. So there are other ways. We can use the derivative, the min-max method, where we take a derivative of k of s with respect to s and set that equal to 0. If we do that of course is one way of doing that. That gives us the same two values as it should, that works very well. Another one that I don't think I've tried before, or I've shown you before, although I've mentioned it, is the trial and error method. And in this method, and let me give a little, there we go, and even things out. We can see that we can take our expression for k of s, okay, it's the same one that we used up here, and if you didn't want to do a derivative, you could say, well, I know where the breakaway point's going to be. I know it's going to be between 0 and -2, So why don't I just put in some values for S that are in between and see which one maximizes the problem. And you can see here at -1 it's 3. At -0.5 it goes lower. At -0.75 it goes up. At -0.85 it goes down a little bit. So we know that it maximizes somewhere around -0.75. Now you might say, well, why isn't it a little higher at 0.85 since it's so close to 0.845? But I think if we tried 0.8, we'd find that it was actually even more of a maximum. So long story short, you can use this trial and error. It's simple in concept. Might require a little bit of work. Okay. So once we do that, we can draw the root locus diagram again, and here it is. And again, you can see, we've got our 3 poles, our branches coming together, and I didn't properly get a good breakaway point on this, but you see it's a little bit better. And remember, that's for k greater than 0. So when k is equal to 0, it's at these 3 poles. When k increases greater than 0, then we see this root locus diagram begin to form. So there you go. That's yet one more example. I probably will do 1 or 2 more to give you some more complex root locus, and see what happens when we have poles not on the real axis.